Besides pressure, we could also measure the volume of the gas. We might know the amount of the gas in grams or moles, and the temperature. And it turns out that all of these properties can be interrelated by something called the ideal gas law, which says that the pressure times the volume is equal to the amount times some constant times the temperature. And so in the stylized images below, there are two scenarios. One is if the pressure goes up, what could have happened given the equation PV equals nRT? Either the temperature went up, the amount went up, or the volume went down. In the graphic at the right, if the pressure went down, it is likely that one of the changes had to occur, and that is that either the temperature went down, the amount of material mass or moles went down, or the volume went up. And so there's a proportional relationship between pressure and temperature and amount, and inverse proportion relationship between pressure and volume. So pressure goes up, volume goes down if the other variables are not changed. So we can use the ideal gas law because if we know three of the four variables, we can calculate the last one. So the ideal gas law enables us to determine some properties given other ones about a set of circumstances. So in order to make use of the gas law, we have to define the proportionality constant R. And so a common value of R involves using pressure in atmosphere, volume in liters, amount in moles, and temperature in degrees Kelvin. And so if one does that, so P times V equals the amount N times R times T. If you look at all those units, and the value for R must be equal to some number of atmosphere liters per mole degree K, and that value is 0.0821 liter atmospheres per mole degree K. So we would use that value R together with the other properties in those particular units. In other words, if we want to solve for some unknown value, we start with the ideal gas law, and we know the value for R, 0.0821 atmospheres liters per mole K. So if we then have any three values for pressure, volume, amount, or temperature, then we can simply solve for the fourth using the ideal gas equation. Let's look at an example of a problem. So it says calculate the pressure exerted by 1.67 moles of ethane, C2H6, in a 25 liter container at 290 degrees Kelvin. So we're asked to calculate the pressure. We're given the amount in moles of ethane. We're given the volume in liters, and we're given the temperature in K. So we can apply the ideal gas equation. In summary, what is known is N, 1.67 moles, V, 25 liters, T, 298 K, and the R value, 0.0821, and what's missing is the pressure that we're calculating for. Starting with the ideal gas equation, PV equals nRT. If you divide both sides of that equation by V, which you're allowed to do by the rules of identity, if you do that, you get P is equal to nRT over V. And so in this particular case, we solve for P by putting in the values for the number of moles, the ideal gas constant, R, and the temperature, and then the volume goes in the numerator. If you multiply these out, you get 1.63 atmospheres as the result. Here's another problem that's fairly similar. Calculate the pressure. So we're looking for pressure exerted by 1.67 moles of ethane, formula given, in 25 liters at 25 degrees C. Now what's known is that we have the number of moles, 1.67, the volume is 25 liters, and the temperature is given in degrees centigrade. We're still solving for the pressure. And of course we know the gas constant, and it's given here because it reminds us of what units we need. So the temperature in degrees Celsius is not the right one. We won't get the right value because the R value is 4 degrees Kelvin. So in order for us to solve this problem, the first thing we're going to have to do is make a change from degrees C to degrees Kelvin. We simply need to find a conversion factor for going from degrees centigrade to degrees Kelvin, and it's very simple. You simply add 273 to the value in degrees C, and you get degrees K, and so that turns out to be 298. It turns out that this question is identical to the one that we already solved. That is, we already solved one for the values 1.67, 25 liters, and 298 K. And so this example just pointed out that independent of what the units of temperature are, we can convert them into a unit that's useful with the particular proportionality constant that we're using for R. This is another variation of the same kind of question. Calculate the pressure exerted by 50 grams of ethane, C2H6, in a 25-liter container at 298. So what's known is that the value for the amount is 50 grams, and grams are not moles. The volume is 25 liters, the temperature is 298, and that the R value, again, is given in atmospheres liters per mole degree Kelvin. So the strategy here is that we have to figure out how to convert from 50 grams of ethane, formula given, to number of moles. And so that's very easy. We actually know how to convert from moles to grams given a formula, and that's the formula weight, or the molar mass. We start by calculating the formula weight for C2H6. There are 2 carbons at 12.01, the atomic mass of carbon, and 6 hydrogens at 1.007, another value that comes from the periodic table. Then if we want to convert 50 grams, we multiply 50 grams times the unit conversion factor. 1 mole is 30.06 grams for C2H6, and that turns out to be 1.67 moles. And so now we have all of our values, N, V, T, in the units that match the constant R, and we can simply plug into the PV equals nRT equation and solve for P. And again, in this particular case, we have another version of the same example that we solved previously, except that instead of giving the amount of ethane in moles, this time we gave it in grams. So we can solve a whole myriad of these kinds of problems simply by converting to the right units.